All right, now let's move to the much smaller memory for our laptop, the SODIMM. Small outline, dual inline memory module. The first one is the 144-pin synchronous dynamic random access memory module. Remember, that's the one-to-one. And that first SDRAM that was small outline in a laptop was 144 pin. Then along came the SODIMM, or small outline DIMM, and they did it for laptops with DDR. It is a 200-pin package. And of course, you take it up to the next level, which is the DDR2. That's a 200-pin memory module package. And then the DDR3 is actually a 204-pin module. So the SODIMM is the small outline. It goes into laptops. And it starts with that first synchronous one-to-one. Then there's the DDR, DDR2, and the DDR3. And what I've given you are the pin counts. You don't have to recognize this stuff by the actual picture, unless possibly they show you multiple memory modules where 2 or 3 of them have a single notch or a key, and one of them has 2 notches. That's going to be the SDRAM that you saw earlier. 90% of the time they'll go ahead and tell you what they're talking about, and they may ask you for the pin count on the exam. Here is the SODIMM comparison, the DDR, the DDR2, and the DDR3. And once again, that key or that notch is different alignment on each one of them, so you can't put the wrong SODIMM into a laptop where it's not meant to be based on the motherboard. From the SODIMM, which is the small outline, now we'll go to the microDIMM. Even smaller than the SODIMM is the micro dual inline memory module. The first one is the SDRAM. That's the one-to-one synchronous, and this one is going to be 144 pin on that module. Then the DDR is 172 pin for the microDIMM that is DDR. Next is the 214 pin DDR2 memory module. And then finally is the DDR3, which is also 214 pin memory module. Now here's a memory module that's a little bit out of the ordinary. It's a Rambus memory module. Rambus is the name because that was the company that was building these memory modules. Sometimes these are called RD, RAM, Rambus, Dynamic Random Access Memory. They may also be called the Direct Rambus, DRAM. And it comes from that company. It is similar in nature to the DDR, double data rate. Remember I told you about the 2 with each front side bus signal? It's similar because it is double data rate and it has 2 channels. Each channel is 16-bit. The thing with this Rambus memory was there was increased latency in the memory. That means it was slowed down, so latency is a slowing of the memory module. It also put out an awful lot of heat. The picture that you're looking at right here, notice it's got that blue shell on top. That's actually a heat sink. So there's a lot of heat output, and the memory module is very complex. This one wasn't marketed very widely, and it wasn't sold very much. Some of you might have heard about some of the really older Dell computers that had this memory. If you did and you decided to upgrade your memory, you might be looking at anywhere from $150 to $200 per memory stick. Why do I tell you this? Because it's on the exam. That's the first reason. Rambus memory is also very unique. You can see from the picture that there are 2 notches or 2 keys, both located fairly close to each other in the middle of this memory module. So this won't fit into any other memory slot at all except the one that is specific, proprietary to that motherboard. Secondly, you might actually find somebody out there who does have a computer, like an older Dell, that has this Rambus memory in there. If you pop it out and you see it has those 2 close notches in that heat sink, tell them right up front it's going to be really expensive and probably kind of hard to find, but it may be on the exam. So be aware of Rambus memory. All right, let's talk about a different type of memory. This time it's not RAM, it's ROM, read-only memory. What we have with an ROM or a ROM memory module is it's read-only because data has been burned to that chip or written onto that chip, and the data doesn't change. Your RAM, your random access memory, is constantly changing. Data is going in and out, maybe new program code is going in and out. It's constantly changing, and that's why it needs that constant refresh of the signal. ROM, on the other hand, is written to in kind of a permanent nature, and it doesn't change. A good example of your ROM chip is your system's BIOS. We are going to talk about BIOS a little bit later in this presentation, but that BIOS chip is on your motherboard, and that BIOS chip is a read-only memory chip. The BIOS has some code burned into that BIOS chip. Part of what's burned into that BIOS chip is something called the POST, Power On Self-Test. Now we'll talk in more details about that later when we talk about BIOS, but the Power On Self-Test is the first thing that happens to your computer when you turn on the power. Literally, this chip, this BIOS chip, goes out and checks all the hardware on that motherboard and everything that's connected long before it ever boots up Windows. So your BIOS is a good example of a read-only memory chip. Those chips started with the PROM, which means it's programmable. That was the first generation where you could burn on or program the contents. Then they decided to make them erasable so they could reuse them, and that was an EPROM, or erasable PROM. And it actually took kind of a special device to erase it. You had to either buy one of those or send the chip away and someone recycle it and then reuse it. The latest version is the EE, which is electrically erasable, programmable read-only memory. Well, that's your current BIOS. And if you've ever heard of somebody saying that they upgraded their BIOS, or they might also say, I flashed my BIOS, the term flash in this case is kind of like a verb. It's what we do when we run a utility that will let us upgrade and change the version of that BIOS chip, because our read-only memory chip can be electrically erased and then completely rewritten with that permanent data on that ROM chip. There's another type of memory. It's random access memory, but this time it is not dynamic random access memory. It is static random access memory. Static doesn't need that refresh signal like the dynamic does. Static memory is more complex. It's also a good bit more expensive, and it is definitely faster than the dynamic random access memory. With static memory, the access times are going to be a whole lot faster as well compared to the dynamic. You could have access times faster or shorter than 10 nanoseconds. The reason why we have this static random access memory is because we often use it in something called cache. That's spelled C-A-C-H-E. Kind of looks like cache. I guess maybe it's a French word. But cache memory uses static random access memory. Okay, so what's cache memory? Cache memory is memory that benefits the performance of your processor. It is static memory, it's faster. But what happens is this: your system is able to predict and prefetch, in other words ahead of time, what the processor is going to need. And it stores that predicted program code or predicted data. It has prefetched and stored it in the cache memory. Now, with the analogy of the cubicle, remember my brain is my processor, my desk is my memory. All of that random access memory down here is this huge desk in front of me. But every time that the processor needs some more data or another execution of a program, I have to reach all the way down to the desk and grab that code and bring it all the way back up, put it into the processor. That's really slow. Wouldn't it be nice if we could just reach all the way down to the desktop, grab some of that program code or data that we have predicted, and we have prefetched it, and I just put it right here in my top pocket? Well, that analogy is similar to what's happening with cache memory. If I can predict and prefetch some of what the processor is going to need, and then I hold it in this temporary spot like my top pocket, when the processor next needs it, it's very easy to just simply grab it right out of my top pocket, put it in. Cache memory is a good example of static memory that helps your processor and your system be optimized. Now, there's different levels of cache, and you want to know this both for the real world as well as for the exam. The first is level 1 cache, often called primary cache. And it's a very small amount of that static random access memory. Level 1 cache is integrated in the processor core itself. Your modern processors, like the one that I've got for my kit, is going to split up that level 1 cache to match the cores. Like for instance, if you have a dual core, it's going to be split into 2 equal caches, one for each of the dual cores in that processor. Those pairs of cores are going to store program data or microprocessor instructions. So you're going to have a pair of those level 1 caches with the core to store program data as well as microprocessor instructions. Level 2 cache is larger. Level 2 cache should be kind of like this. If level 1 cache is my top pocket, how about if level 2 cache is a fanny pack? I don't know if everybody here is old enough to remember fanny packs, those things that go around your waist, a little belt buckle. Never mind. If you're not old enough, it's a little pouch down there. It's bigger than my top pocket of my shirt, but it can hold a lot more. And that's what level 2 cache is. The placement of the level 2 cache has changed over time. Recently, you'll find all of the level 2 cache right up there in the processor core. It is integrated. It's what's called on-die with the processor. If we go back in time to the days of the Pentium Pro or the Pentium 2 or the Pentium 3, you might find that the level 2 cache was in the same cartridge as the processor, but it was actually separate from the processor itself. If you went back to the really old legacy systems before the days of the Pentium 2 or the Pentium Pro, then this level 2 cache would actually be stored down on the motherboard itself, completely separate from the processor or the processor cartridge. Well, then finally there's level 3 cache. It's larger than level 2 cache. Level 2 cache has often been integrated into the processors I mentioned a moment ago, and in some of our legacy systems, level 3 cache would be on the motherboard. Now, if I take it back to my analogy of the cubicle, level 1 cache is my top pocket, level 2 cache is my fanny pack, level 3 might be a big old backpack on my shoulder. But the point is, I can scoop up an awful lot of stuff from main memory and populate these different levels of cache to speed up the system. The newest processors, the level 3 cache is also on the CPU chip. Okay, now let me tell you about the kit that I'm building. You've seen the motherboard so far for that kit. And the CPU for that kit is an Core, it's an Intel Core i5-3450. That is a quad core, 4 cores. That means that I have 4 level 1 caches. Each of them is 32K or kilobytes. I have 4 level 2 caches, and each of them being bigger is 256 KB. And then my level 3 cache is actually 6 megabytes that is shared across all 4 of the cores. So my specific processor is a quad core. It's the i5-3450. And this particular model of that i5 has 6 megabytes that's shared across all 4 of the cores. I believe earlier when I was talking about processors, I might have said that my processor was 4 megabytes. There are some of the i5 series that are 4 megabytes because it's a range between 4 and 8. My particular model is 6 megabytes on the processor that I have in my kit. So level 1, level 2, and level 3 cache go from small to medium to large. The purpose of cache? Well, remember, it's static memory. It speeds up the processor, and in the case of my kit, it's 32K on the level 1, 256K on the level 2, and 6 megabytes shared across the 4 cores in level 3 cache.